Test, 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 test. So we will start now. Sorry for the delay. There is one speaker who's still not here. That's the second one. My name is Florin Rus, and I'm the session chair of this session on interactive data exploration and approximate query processing. We have 3 papers. There are 100 minutes allocated to the session because there are other sessions with 4 papers at this time. So I decided to give all the speakers all the time, half an hour, no hurry. Anyway, there is empty time at the end. As I said, 3 papers. First paper is 2-level sampling for joint size estimation, and Yu-Chen is going to present the paper.
Thanks for the introduction. So the problem we work on is to estimate join size. And I will first introduce a problem. So in this talk, I will mainly focus on two-table join. The most common two-table join includes a primary key, foreign key join. So you are given two tables. In this example, you are given a customer table and an order table. The customer key for customer table is the primary key, and the customer key serves as a foreign key for the order table. So when you join these two tables by the customer key, you get a list of orders with full information of the customers. So this is a primary key, foreign key join, and the relationship is one-to-many. And the many-many join is another common thing two-table join. So in this example, we have a Twitter following relationship table. So in this table, each tuple is contains a follower ID and a followee ID, which describe a follow relationship in this social network. So the first tuple 1, 2 means that user 1 follows user 2. So there is a direct edge from node 1 to node 2. So this table will describe that follower-followee relationship. So when you want to query about all such relationship, A follows B, B follows C, you will join this table with a logical copy of its own T2. And this query T1 join T2, where T1's followee ID equals T2's follower ID, will give you all the relationship A follows B follows C. So it's, this is a many-to-many join. And join always comes with selection predicates in practice. So in this example, we want to join customer with order where the age of customer is smaller than 35 and the total price of the order is greater than 200. So this is the query we want to find out. But know that these selection predicates are only given at query time. Although the primary key foreign key relationship are given when you are given the data scheme, but the selection predicates are only given at query time. Then our goal is to estimate join size at query time with the CA and CB as the predicates given at query time for table A and table B. And here I will introduce some notations. Here we use capital BV as the set of tuples in table B with join value V. So in this example, B2 is the set of the orange tuples, and the size of BV, of capital BV is denoted as BV. So in this case, B2 equals 2 because we have two tuples with join value 2. So the size is 2. And we denote the vector of the frequency of each tuple as the frequency vector A and B, and we often use the LP norm in the following talks. So now we understand our goal is to estimate the join size, which is sigma AVBV. Okay. And there are many works has been done in the literature to solve the problem. There are 3 main approaches. The first one is sketching and the synopsis and random sampling. So for sketching-based method, we build one sketch for each table on the join attribute, and they usually give very accurate estimates for join without predicates. But how do they dealing with selection predicates? They build sketch on imaginary table at query time when they are given the predicates. So we back to the formal example. When you do a query for customer join order with predicates on both tables. They make imaginary tables according to the predicates given. So for age smaller than 35, they make an imaginary table contains every value that satisfies the condition. And for total price greater than 200, they made another imaginary table contains all values that satisfy the predicates. And then they build a sketch on this imaginary table. Then they do the estimation, use the sketching method. They treat this problem as a four-table join. So the two-table join problem becomes a four-table join problem when two predicates are given accurate time. And then the error grows rapidly in this case. And also, this method only supports equality and range predicates. It does not support complex predicates or user-defined functions. For synopsis-based method, they are using statistics, histogram, wavelets, and heavy hitters. They will build a synopsis on the multi-dimensional space defined by the attribute. So here is an example for table A. They has two attributes, A dot X and Y, and they use a lossy compression on the on the two-dimensional space formed by the attribute. So here each range means that there is, for example, the 2 means that there is 2 tuples in this range. And when you are given a predicate at query time, you will use this synopsis to give an approximation how many tuples are in this range. And this method also only supports range and equality predicates. And when the data are sparse, the effectiveness of compression will be very low. Till now, we only seen experiments on a four-dimensional space, and the domain size is small, 64. The third method is random sampling. This is more like an all-purpose approach, because for any predicate CA on table A, we can directly apply the predicate to the sample and use the sample that satisfies the predicates to estimate the join size at query time. So we can collect samples offline without worrying about the predicates and give estimation at query time. And the sampling is insensitive to domain size, the form or number of predicates, or the sparsity of data. So the most direct method one can consider is to use independent Bernoulli sampling, which is just sample each tuple independently with probability Q. So in this case, we sample each tuple with probability 1/2, and we do the same for all the tables. And then we join the samples to get, so we denote the sample for table A as SA and for table B as SB. Then we join these samples and use the sample size of the sampled tuple scaled by 1/Q² to get estimation for the join size. Because each tuple in each table is sampled with probability Q, then it will appear in SA join SB only when they are both sampled for table A and table B. So the probability is 1/Q². Then when we scale it by 1/Q², we get an unbiased estimator for the join size. But these tuples in SA join SB are not independent, so the variance is a little bit complex. So here is a variance for this estimator. And the problem for this method is that this method sample each tuple independently, so they ignore the joint relationship between the two relations. And another method, sampling-based method called correlated sampling. It uses a hash function to establish the relationship between two tables. So it defines a function h from the domain of the join attribute, from the domain of the join attribute to 0 to 1. And every tuple with join attribute value v is taken into the sample if hv is smaller than p. So hv, the probability hv is smaller than p is p. Then in this example, we have h1 and h3 is smaller than 1/2. Then all tuples with value 1 and value 3 will be taken into the sample. And then we join the samples and scale the join size of the samples by p to get the unbiased estimator for the true join size. This is because a tuple with value v will appear in the join result of the sample if hv is smaller than p, and the probability of that is p. So we only need to scale the sample size by p. That is the correlation established by the hash function. And the variance is as follows. So these two methods, there is no definite comparison between these two methods. So I will give two extreme examples to compare them. So here in this example, the join between A and B is simply 1-to-1 map, an extreme case. Then in this case, Bernoulli sampling, because it independently sample every tuple with a small probability, it does not care about the relation. Then it has trouble matching the tuples, although it samples a lot, but in the joint result, there may be only little tuples. So Bernoulli sampling in this case has large variance than correlated sampling. And the second case, the second extreme case is that all the joint tuples in two tables share the same value. Then the joint between A and B will be a Cartesian product of these two tables. Then in this case, correlated sampling, because it have the same value, then correlated sampling will take them all, or takes none. It will sample all tuples with probability p, or sample nothing. So it will has very large variance in this case. So to conquer their drawbacks, we propose our new algorithm called two-level sampling. For the first level, we also use a hash function to establish the relationship between two tables. So we use function h from the domain of the join value u to 0 to 1. And for each value v, where hv is smaller than p, one tuple in so we sampled value v, but we does not take all. We take one tuple in AV as the sentry, and for the rest, we does not take it all. We goes to level 2, and we sampled independently with probability q to get the blue tuples as AV. So for the first level, we use correlated sampling to sample the value and take one sentry. And for the second level, we use Bernoulli sampling to sample from the values that we have chosen in level 1. And the same is done for another table, table B. And then this is an unbiased estimator for the join size. So the here SAV and SBV are not independent because the correlation on the first level, but they are independent condition on V is sampled. So we can so EXY equals EX times EY condition on V is sampled, and the number of blue tuples we sampled in the second level is follows the binomial distribution, so it is Q times AV minus 1. 1 is for the sentry. Then this becomes an unbiased estimator for the join size. And here is a variance for our two-level sampling estimator. And the algorithm can be easily performed in one pass over the data because we can use reservoir sampling to sample the century by a one pass over the data. And apparently Bernoulli can be performed over one pass. Then two questions arise. So how to set our parameters P and Q? The first level probability P and the second level probability Q. Then this becomes an optimization problem. We want to minimize the variance of our estimator while the sample size is fixed. And we assume that we are given basic statistics. So A0 is basically the number of distinct values in table A, and A1 is the size of table A, etc. And we compare the variance of all the existing sampling algorithms while the sample size is fixed. And we compare this method for primary key foreign key join where BV equals 1 for all V in B, and for many joins. For we can see that when the second level sampling probability equals 1, our two-level sampling method degenerates into the correlated sampling because we do not do sampling for the second level. Then as long as we can find optimal P and Q to minimize the variance, our variance is almost always smaller than correlated sampling. So in primary key foreign key joins, we can find the optimal solution for P and Q. And our variance is smaller or equal to the variance of correlated and smaller than the Bernoulli sampling. But how much small? So the ratio between our variance and the correlated sampling variance is approximately the sum of two terms. The first term, B1 over A1, describes that the larger the foreign key table is, the better our two-level sampling algorithm is. And the second term is that the higher skew the foreign key table is, the better our two-level sampling will perform than the correlated sampling. And in practice, because foreign key table are in practice are always much larger than primary key table, so we always has this stance. And we also do experiments on primary key foreign key joins on TPCH benchmark data, where we run each estimator 500 times, and we measure the relative error of each time, and then we take the median error and the 90% quantile error and show them on the graph. So in the graph, you can see that two-level the error of two-level sampling is much smaller than correlated and much smaller than Bernoulli. And as sample size becomes larger, the error drops. And we also do experiments on TPCH data where one predicate is given. And here's a experiment result. And this is for join with two predicates. And in all the cases, our two-level sampling outperforms correlated and Bernoulli. And as TPCH data are almost uniform, so we regenerate TPCH data to get a skewed data. The foreign K the frequency of the foreign K value follows the ZIP-F distribution, and the distribution, the skewness is controlled by the ZIP-F parameter alpha. So as alpha becomes larger, the data is more skewed. So as you can see that as the data becomes more skewed, the error grows, but two-level sampling grows slower than the other method, and the error is much smaller. And for many joins, the optimal parameter for our two-level sampling can also be found by solving a degree 4 equation. And as long as optimal parameter can be found, we are better than correlated. And the ratio between two-level and correlated is smaller or equal to 1 asymptotically. And this term means that the higher screw the joint result is, the better our two-level sampling. But there is no definite comparison between two-level and independent Bernoulli on many joints. In fact, when we apply our two-level sampling to Twitter data, it does not perform better than Bernoulli sampling because it treats every value with the same importance for the first level. So we are thinking about using frequency information to improve the accuracy of our sampling. An algorithm called unbiased sampling was proposed. It is a frequency-aware version of correlated sampling, and it favors joint value with higher frequency, which means that if a value appears much time in the tuple, we should sample more. So it is a frequency-aware version of correlated sampling in that for the first level, it uses a p-way for each joint value way, and the probability way is sampled is proportional to the frequency of that value. So p-way is proportional to a-way in unbiased sampling. So in this case, for the first table, as every customer K appears one time, so we sample them with the same probability. But for the foreign K table, you can see that customer K2 appears 4 times, while the others appears 1 times. So the probability is 1 for customer K2 and 1/4 for the other values. So unbiased favor value with higher frequency. So in this way, we can also develop our frequency-aware two-level sampling, where we use p-way as the first-level sampling probability for each value way. And the optimal Q can also be found by numerical method. And given Q, we can decide p-way for each value way. By setting Q to 1, so if we do not do the level 2 sampling, p-way should be proportional to a-way b-way over square root of a-way plus b-way. So that is the result. So from our analysis, we know that for primary K, foreign K joint, p-way should be proportional to square root a-way. And for many joints, p-way should be proportional to a-way to the power of 1.5 when a-way equals b-way. So from the result here. None of these cases match the choice of unbiased sampling, because unbiased sample values proportional to a-way, while our results show that we should sample proportional to square root a-way for primary K, foreign K joint, and a-way to the power of 1.5 for many joint. The intuition here is that although tuples with value way contribute a-way to the sample size, but it will contribute a-way square to the variance. So so to achieve smaller variance while the sample size is the same, we should sample proportional to square root a-way. And for the second case, the intuition is that although tuples with value way contribute a-way to the sample size, but they contribute a-way to the power of 4 to the variance. So we should sample to the proportional to a-way to the power of 1.5. And with the frequency knowledge given, we have our two-level frequency-aware version. And you can see that for the same experiment on skewed data, as the data become more skewed, the two-level frequency-aware performs much better, the purple line, than all other methods. And this time, two-level with frequency known defeat Bernoulli sampling also on Twitter data. So a brief summary of my talk. So we build upon and extend 3 sampling algorithms: Bernoulli sampling, Curtis sampling, and Bass sampling, and give our new sampling algorithm 2-level sampling, which achieves a smaller variance for both primary key joins and many-to-many joins. And we also give confidence interval to our estimator. So when the algorithm gives you estimation, you know how good it is. And we extend our method to sum and average queries to support sum and average queries. And we extend our method to chain joins and star joins. So that is all. Thanks.
Any questions?
So very nice work. So at the beginning of your talk, you mentioned that 2-level sampling only need to go through the data once.
Right.
But it's not clear to me how the frequency-aware sampling techniques can get the frequency and also do the sampling with one part of the data.
You mean for... So this is a frequency or noise version of 2-level sampling. So we do not need to know the frequency for every value. We only need to know the size of the table and distinct the value in the table to decide our P and Q. That is all we need. Then we can do the sampling. For frequency aware version, so for frequency aware version, we first compute PV, because frequency aware version assume that frequency are knowns. So in our experiment, we only need the heavy hitters of all the frequencies. Then we can solve the optimal Q for the second level probability, and we solve and we compute PV. When we see a value V, we compute PV, then we know the probability we should sample it. Yeah. Yeah.
That's how the original algorithm was also defined. Over flows of packets that are aggregating packet information that is loaded. Any other questions?
Thank you for the presentation. Are these samples pre-computed before the query comes in your case?
Pre-compute? I'm sorry.
Do you construct the samples before the query time, or?
Right. We do the sampling offline. So
Okay.
when you load the data and use the sample to answer query at query time.
So you're also assuming that you know the join keys in advance.
Yeah, because the data for database the scheme are often fixed. They don't. You know the foreign key primary key relationship. You know which attribute will join which attribute beforehand.
Yeah, but you don't know that for many.
Many.
Yeah, many-to-many joins.
Right, but for our example, for the social network, that is the query. You know the frequency which query will be asked.
Any other questions? Then let's thank the speaker once more time. The second paper is titled General Purpose Counting Filter, Making Every Bit Count. The presenter is Prashant Pandey from Stony Brook University.
CQF. Yeah, this one. Yeah, CQF. I'm Prashant from Stony Brook University. Today, I'm going to talk to you about a new data structure known as the counting quotient filter. Counting quotient filter is a type of an AMQ data structure that is approximate membership query data structure. So let's begin by learning how an AMQ data structure works. AMQ data structure is a lossy representation of a set, and it supports operations like insert and query. And it often takes like less than 1 byte per element, but the space savings comes by the fact that it occasionally returns a false positive answer. And I'll talk to you about what that means in the later slides. Now let's talk about one of the most common and most used AMQ data structure, which is a Bloom filter. How does it work? It's okay. Yeah. Okay. So a Bloom filter is a simple data structure. It is a combination of a bit array, like m-bit array, and so Bloom filter is a combination of an m-bit array and k hash functions. So right now in the array there are no elements, so all the bits are like cleared out. To insert an element, you do a simple thing. You hash the element k times, and you go to the locations, and you set those bits in the data structure or in the bit array. To insert another element, you do the same operation, and you set those bits. And similarly for the third element. You can see here that element x shares the bits location with element w and element y. Now let's see how do we query in a Bloom filter. To query, we do the same operations as an insert. We hash the element k times, and we probe all those locations. And if all those locations have a bit set, then we know that element is there in the Bloom filter. So here, since w is in the set, both these bits are set, and it will return yes. What if you query for an element u, which is not there in the set? So you hash it k times, and you go probe on those locations, and you see that one of the locations is 0. That means that element is not there in the set, and the returns value is no, which is a correct value. However, if you query for another element, z, which is again not there in the set, but the hash locations, both the hash locations have a bit set in the data structure. In this case, the Bloom filter will say yes, that it is there, but actually it is not there. So that kind of a result is a false positive result. The Bloom filter has a bounded false positive rate, and there are no false negatives. Bloom filters are ubiquitous. They are used across applications in different domains. For example, they're used in databases, storage, networking, computational biology, and other domains as well. So Bloom filters are one of the most successful data structures. Now let's see, what if you want to represent an AMQ not just for a set, but for a multiset? Here is a new kind of a data structure known as a counting filter. A counting filter is a lossy representation of a multiset, and it supports operations like insert, query, which are same as an AMQ for a set, but at the same time, it also supports deletes and the count operation. You can query for the count of any particular element. The overcounts in the counting filter are analogous to a false positive. As I said, that they're compact representation of a multiset. That means they occasionally return overcounts to element, which is like same as a false positive answer in a Bloom filter. Okay, let's see why is counting important. There are many applications that want counting. For example, there is schema counting application in computational biology. You want to do some anomaly detection in a networking application. You may want to count the n-grams in a natural language processing application. So all of these applications, they need counting data structures. And also, counting enables us an AMQ to support deletes. And I'll tell you how it works. The one thing important to notice here is that all these applications that I just talked about, schema counting, anomaly detection, and n-gram counting, all of these applications, they deal with real-life data sets. And most real-life data sets are skewed. For example, here is a data set. It is an RNA sequence data set. And you can see the x-axis tells you the given frequency of an element, and y-axis tells you the number of items occurring with that frequency. You can see on the left-hand side of this graph, there are at least 1 billion elements that occur with a count of 1 or 2. And you can see on the right-hand side of this graph that there are very few elements that occur with a very high count. So there are 1 or 2 elements in the data set that occur like, say, a few million times. I mean, there's a blue line here, but it's very small, so you can't see it, but it actually goes to like 10 million. So counting filters should handle skewed data sets efficiently, because when applications deal with real-life data sets, they need to be good to deal with skewed data sets. There have been variants of Bloom filter that try to count elements in a data set. For example, there is the counting Bloom filter. In a counting Bloom filter, we replace the bit array by an array of counters. And Bloom filters were invented to support deletions in a set. For example, when you represent a set, there are not a lot of repetitions. So what happens is that when you want to delete, you don't have to make the counters large enough. Most practical applications only use like 4-bit counters in the counting Bloom filter. And the operations are pretty similar to a Bloom filter, but instead of just like setting the bits, you increment the counts and the counters. But now let's see, what if you want to adapt a counting Bloom filter for like any skewed data set? For example, if we use the counting Bloom filter for the same data set we just talked about, a counting Bloom filter will take like almost 38 gigs of space, and it is very high space. Now let's see, can we do better here? So this paper or this talk, we're going to introduce you to a new data structure known as a counting quotient filter. Counting quotient filter is precisely a replacement to a counting Bloom filter or even a standard Bloom filter. It is space and computationally efficient. And the main thing here is that it supports variable size counters to handle the skewed distributions. From that, I mean, the space usage of a counting quotient filter is always smaller than or equal to the space of a standard Bloom filter, which does not count, plus the space to represent all the counters in an optimal form. So the space is basically summation of log of all the count values of all the elements, so which is asymptotically optimal. For the same data set we just talked about, if you represent that data set using a counting quotient filter, it will take about 2.5 gigs of space, which is like much better than a counting Bloom filter. There are some other features in the counting Bloom filter. Let's just talk about them. They are smaller than many non-counting AMQs. For example, they're smaller than a Bloom filter, a cuckoo filter, or a quotient filter. They have good data locality, so they're easy to scale out of RAM. They can even go to disk and still do good in the performance, like inserts and delete performance in the queries. They support deletes like any other AMQ which supports the multisets. They can be resized dynamically, and they are mergeable as well. So they support all these features, which are like a standard AMQ features and also needed in many applications. There's some other contributions of the paper, which I will quickly go through. The new quotient filter has a new metadata scheme, which is the counting quotient filter, and it uses less number of metadata bits compared to the original quotient filter data structure. It supports the variable length counters, as I talked before, to encode the counters, and it works very good even for a skewed distribution. And we do not have any overhead to store those counters. Like, we just store those counters, but we don't have any extra overhead. And at the same time, we use new x86 instructions to implement the metadata manipulation operations in the data structure, which can also be used in other data structures that have the same approach of rank and select operations. In this talk, I'm going to go talk more about the variable length counter encoding scheme, and for the other two contributions, you can take a look at the paper. Now let's go down and see how does quotienting work, which is the main approach behind the counting quotient filter. Quotienting is an alternative to Bloom filters. What we do is that we store the fingerprints compactly in a hash table. You take an element X and you hash it, and h of X is its fingerprint, and we store that compactly in a hash table. So what happens is that the only source of a collision or a false positive is when two distinct elements, X and Y, have the same fingerprint. In that case, if X is there in the set and Y is not there in the set, and you query for a Y, then the result will be a false positive. Let's see how we store the fingerprints compactly. What we do is that we split the fingerprint into two pieces. The high order Q bits is known as the B of X, and it is the bucket index, or it gives us the index in the hash table where we want to store information. And the lower order R bits is the T of X, also called as tag, is the information that we actually store in the bucket, in the hash table. For example, if you have an element U and you want to store, so B of U will give you an index in the hash table, and T of U is a tag that you're actually going to store in that bucket. The higher order bit here is that we do not store the higher order bit. The higher order Q bits are stored implicitly in the data structure. Now let's see what if there's another element V which hashes to the same bucket. How we deal with this kind of a collision is that we use linear probing. We store the tag of element V in the later slot. But now the issue is both T of U and T of V, the tags of U and V, have the same home bucket, which is the index 4 here. And if you just look at the hash table, how do you know that the tag of V belongs to bucket 4 or bucket 5? Because it may have been shifted down, or it may have been actually indexed at location 5. So to resolve all these collisions in the counting quotient filter, we use 2 metadata bits per slot. The 2 metadata bits helps us to resolve the collisions and at the same time identify the home bucket of each and every tag in the data structure. The metadata bits help us to group all these tags together by their home bucket. For example, all these tags in the red are storing the information for this home bucket, which is here, but they're not stored in their home location. So they're stored in the later slots. Similarly, the green slots here, they store tags for X and Y, but they actually hash to a bucket here, which is this one. So we use 2 metadata bits to identify the home bucket of each and every tag in the data structure. So the metadata bits enables us to identify the slots holding the contents of each bucket. Now let's see how we count. Well, this is not a very good explanation how we count, but let's go and see how we actually count. As I told before, like we have the metadata bits, and the metadata bits helps us to understand or identify that these slots in the data structure or the hash table store the information for this home bucket. Like all these, the red slots are holding the information for this home bucket. They all hash at this bucket, but they're stored in a different slot, later slots. Similarly, the green slots are holding information for this home bucket. So using the metadata bits, we would know that any contiguous set of slots in the data structure to which like these slots hold some information for some other home bucket, and we can know that information using the metadata bits. Now, how we store the information or tags in that range or set of slots, it depends on us. We can do whatever we want because the metadata bits helps us to know these slots belong to which home bucket. But if we want to count, in the original quotient filter paper, they counted in unary. From that I mean, if a tag of U appears 4 times in your data set, it will be stored in 4 consecutive slots, and it will consume 4 slots. So that is counting in unary. However, this kind of counting is not very efficient because it won't work if you have a skewed data set wherein one element occurs like millions of times, and this will take millions of slots. So what we want to do is that we want to encode the counts in binary and not unary. The idea is we use the space which is reserved for tags to actually store the counts. For example, you can see in this slide, TU, the tag of U, was stored like in 4 different slots. However, now we store tag of U only once, and we store the information about the count in the next slot. And since we have the metadata bits, it helps us to identify that these 2 slots contain the information for this home bucket. And similarly, the tag of X appears only once, and tag of Y appears only once. And we can use the metadata bits to identify that all these four slots contain the information belonging to this home bucket. But the issue is, if we want to do that, how do we identify the information or the information stored in this slot is a tag or a counter? To do that, someone might use a control bit, but we don't want to use any control bits. As you remember, I said in the early slides that we do the counting even for skewed data sets without using any extra overhead for counting information. If you want to know about how we do that, you might have to go and look at the paper. Now let's look at some evaluation. Here are two graphs. On the left-hand side, you have the insert throughput, and on the right-hand side, you have the lookup throughput. It's the throughput, so higher is better. On the x-axis, you have the load factor, like how full is your data structure. So 20 means like 20% full, and 80 means like 80% full. You can see we compare the counting quotient filter against 2 different data structures. One of them is a cuckoo filter, which is a state-of-the-art AMQ, and another one is a Bloom filter, which we already talked about. Both these experiments are done on a uniformly random distribution data set. You can see the performance, the insert throughput of a counting quotient filter is competitive to the performance of a cuckoo filter, even though a cuckoo filter does not count. And you can see at a higher load factor, the counting quotient filter is actually faster than the cuckoo filter. And for the lookups, the performance of counting quotient filter is faster than the cuckoo filter for a load factor until 75%, and after that, it is a little slower. And for both the experiments, counting quotient filter is always faster than a Bloom filter. Now let's see, when we did the evaluation on a skewed data set, comparing the counting quotient filter against a counting Bloom filter. The experiments are pretty much the same. Like on the left-hand sides, we have the insert throughput. On the right-hand side, we have the lookup throughput, and higher is better. And the x-axis is the load factor. The data sets here are skewed, and they are generated using a Zipfian distribution with a constant of 1.5. You can see for both the inserts and lookup throughput, the counting quotient filter is 6 to 10 times faster than the counting Bloom filter. And for this data set, the size of the counting quotient filter is 15 times smaller than the size of a counting Bloom filter for a same error rate. And the error rate in these 2 configurations is 0.001. And from error rate, I mean the false positive rate. So to conclude my slides, or my talk, the CQF is a smaller data structure compared to other non-counting AMQs, and it is faster than Bloom filter, and it is competitive to the cuckoo filter, which is again a non-counting data structure in terms of inserts and lookups. The CQF supports many features, like it supports deletes, resizing, cache locality, and other features that modern applications need. And at the end, we want to say that the CQF demonstrates that the design of a quotient filter is extensible, that we can store much information using the metadata bits in the slots that are actually like reserved for the remainders or the tags. And the code is available open source. You can go and use it in your applications. And you don't have to take our word. At least half a dozen teams across computational biology and streaming applications are already using this data structure. And it is in place of a Bloom filter or a counting Bloom filter, and the numbers are reproducible. Like they say that they have the same kind of the benchmarking results are pretty much the same, so they get the same performance that we get in the paper. So that's all from me, and I'll take questions now.
Any questions?
I think it's clear. So I didn't get the linear probing part of of your talk. So for two reasons. First, how do you wrap around at the end of the filter, and won't that screw up your metadata bits? And then also, if you have to insert something in between, do you push all the other values down the filter, or what do you do when you had the value with and then the 4, and now you have a new value that you want to insert there, but there's no space, so you'd have to skip there or with your.
Yeah. So you have two questions. The first one is, how do you wrap around? So the quotient filter, like, you create the number of slots based on the number of distinct elements in your data set. So even if something hashes here and some more things hashes in the last slot in the data structure, you can wrap around. But in that case, you have to do the mod operation every time, because you need to know the limit of the size of the number of slots. So what in practice we do is that we allocate some extra buffer space at the end of the data structure. So even if the last few slots overflow, we can accommodate in the buffer space, which is like small. Like I don't remember exactly how small it is, but it's not like even it's a constant factor of the actual space of the number of slots. And the second question is that, what if you insert something in between? Yes, we have to shift, like in this case, if there was a new element coming in here, which belonged to this bucket, then the slots or the tags stored in the later buckets have to be shifted down one slot, and this new element will go in the location or in the region of tags where it belongs.
What kind of hash function do you need to use? Because I think if you use linear probing, generally require stronger hash functions to work, right?
Yes, I mean, we use a uniformly random hash function. For these experiments, we were using murmur hash, and it's pretty fast. Like, you just use a hash function that can give you a uniformly random permutations to the domain value.
So the analysis assumes it's truly random. It's
yeah.
Okay.
Yeah.
Other questions? Actually, I have a question, because you mentioned that you need to know the number of distinct elements before you build your data structure. Is that true?
I mean, you need to know some, because you configure your data structure depending on, so it's
number of distinct elements. I mean, that's a pretty strong assumption that you have at the beginning.
I mean, you need to know like number of elements. So what happens? Okay, so let me explain you in a better sense. So what happens is that you know that we use the fingerprints, and the size of the fingerprint is like, say, P, and we split the P into two parts, Q and R. So the Q part here, you can see that it gives you the number of slots you will have in the data structure. In the hash table.
That I understand, but you said that the total number of, the number of distinct elements in your set that you will try to put in the Bloom filter is related with this size. Is that true?
Yeah.
Okay. Thank you. Other questions? Okay, then let's go to our last talk, which is. Where's the applauses? So our last paper is called BPI, Fast and Memory Efficient Method for Billion Scale Random Walk with Restart. The talk will be given by Jin-Hong Jung from Seoul National University.
Hi, do you hear me? Hi, I'm Jin-Hong Jung at Seoul National University. Today I introduce our paper, BPI, Fast and Memory Efficient Method for Billion Scale Random Walk with Restart. This is joint work with An-Yong Park, Professor Lee, and Professor Kang. Okay. Okay, random walk with restarts measures the relevance score between nodes in a graph. It has been used in many data mining applications based on graphs such as recommendation, and normal detection, and subgraph matching. So random walk with restarts is important tool for graph analysis. Random walk with restarts measure node relevance score using a random surfer. The surfer starts at query node S on a graph, And at each time, the surfer decide one of the following action. The first action is called random walk. That the surfer moves to one of the neighbors with probability 1 minus c. And second action is restart, that the surfer jumps back to the query node S with probability c. So RWR computes the stationary probabilities that the surfer stay at each node. So as shown in this example. And in this example, the query node is 2, and the RWR score with respect to the node 2 are in the table. So let me explain the problem definition on RWR. Given an adjacency matrix A and the query node S and the restart probability C, our goal is to find the RWR score vector RS with respect to the query node S, satisfying the following recursive equation. In this equation, the middle term indicates the random walk, and the last term indicates the restart. So, yeah. And actually, the computing RWR is equivalent to the solving a linear system. So if we move this term into the left-hand side, and if we group them by RS, and it is represented as follows. Then if we define this term by H's, and this equation represents a linear system on H's. So given H's and QS and the restart probability C, we can obtain the solution RS by solving the linear system on H. There are two types of existing methods for computing RWR. Iterative method iteratively updates the RWR score until convergence. For example, power iteration computes the following update to rule at each iteration. The method do not have pre-processing phase. And in query phase, given QS, the method repeats the update to rule until convergence. Pre-processing methods compute the RWR score directly from pre-computed data. For example, inversion compute the inverse of the matrix H's to compute the RS. So in the pre-processing phase, the method computes the inverse of H's, and in query phase, the given QS, the method compute the RS based on these pre-computed matrices. So our research question is, how can we compute RWR query quickly on very large graphs? The advantage of the iterative method is that they scale to very large graph because they do not need pre-computed data. But they show slow RWR computation speed because the whole iteration needs to be repeated for each query node. The advantage of pre-processing method is that they show fast RWR computation speed because they directly compute the scores from the pre-computed data without iteration. But they cannot handle very large graphs because they require heavy computational cost and memory consumption. So main challenge is that how to devise a fast and scalable algorithm for computing RWR score. Okay, let's check our proposed method. We propose BEPI, which stands for fast or pre-processing and iterative approaches. BEPI is a fast and scalable method by taking the advantages of both pre-processing and iterative approaches. Our key ideas are summarized as follows. Let me explain the idea step by step. Our first idea is to exploit real-world graph characteristics to adopt a pre-processing approaches for fast query speed. More specifically, we reorder node IDs to permute H's based on the dead-end and hub-and-spoke structure, which are real-world graph characteristics. After that, we apply block elimination as a pre-processing approaches. Let me explain the concept of dead-end reordering. Dead-end is a node having no outgoing edges. So for example, a file or image having no outgoing links is a dead-end in web document networks. So in the dead-end reordering method, we assign high node IDs to the dead end, we assign row node IDs to non-dead ends. So the original matrix H is parameterized like this. We also exploit the hub and spoke structure. According to the previous work, the entries of H's are concentrated by reordering nodes based on hub and spoke structures. In the hub and spoke structures, hubs are high degree nodes and spokes are low degree nodes. And there are few hubs and a majority of spokes in real world graphs. In the hub and spoke reordering method, we assign high node IDs to hub, and we assign low node IDs to spokes. So the original matrix is parameterized like this. So we combine the dead end and hub and spoke reordering methods as follows. We first apply dead end reordering method to the original matrix H's, and then we apply the hub and spoke reordering method to this part. So we finally obtain this reordered matrix like this, which is a 3x3 block matrices. So the original linear system is represented by a 3x3 block linear system, and this equation H11 is a block diagonal matrices as shown this figure. So after that, you apply block elimination as a pre-processing approaches. So if you are interested in the derivation of the result, please see the lemma 1 in our paper. The point is that you can compute the solution using this equation. And in this equation, S is called the short complement of H11, and S is computed by this combination of the submatrix in H's. The point is that if we pre-compute the blue color rhythm matrices, and then we can compute the RWS score directly from these pre-computed matrices. So we can make the RWS computation fast through these pre-processing approaches. Okay, let's check the second idea. Second idea is to incorporate an iterative method into the pre-processing approaches to increase the scalability. Note that in this equation, we need to compute the inverse of H11 and the inverse of the short complement S. So computing the inverse of H11 is trivial since it is a block diagonal matrices as shown in this figure. But inverting S is impractical in very large graphs because the number of hubs is greater than 1 million in a large graph, and the dimension of S is equal to the number of hubs. So for example, there are 10 million hubs in Twitter networks used in our paper. So we cannot compute the inverse of S in very large graphs. So our solution is to solve the linear system on S using an iterative linear solver. Let's focus the equation on R2 from this equation. If we move this term into the left-hand side, and if we define this term by Q2 tilde, then this equation represented by a linear system on S. So if we use an iterative linear solver, we can obtain the solution R2 without inverting S. So introducing the linear solver increases the scalability of RWS computation. Okay, let's check the third idea. Third idea is to optimize the performance of iterative method to accelerate RWS computation speed. Thus that iterative method solve the following linear system. The running time of linear system is proportional to the number of iterations and the number of non-zero of the S. So our optimization technique aims to answer the following question: how to decrease the number of non-zero of S and how to decrease the number of iteration. Let's check the details of the optimization. Before going on, we need to understand the hub and spoke reordering method because the first optimization is based on tuning the parameter used in this method. So hub and spoke reordering method is used to reorder the original matrix H like this. So in the hub and spoke reordering method, for each iteration, the method select the hub with a hub selection ratio K. So the method disconnects the selected hubs and assign node IDs for hub and spokes. And the method repeats the above procedure in the next to GCC, which is a giant connected component. In this example, K is 0.07, which is a hub selection ratio, and the number of nodes N is 14. And the method selects the set of the K times N hub for each iteration. In this example, the set of the K times N is 1. So at step 1, the method selects the highest degree node, like this red one, and disconnect the red node from the graph, and the graph represents like this. The method assign low node IDs to the spoke, and assign high node IDs to the hub, and the method assign the middle node IDs to nodes in GCC. So the point is that according to the hub selection ratio K, the number of hubs selected by the method can be changed. Okay, let's go back to the discussion about this. Okay, the first optimization reduced the number of non-zero of the short complement S in this linear system. As I mentioned previously, according to the hub selection ratio K, the number of hubs can be different. So if we change the hub selection ratio K, then the number of non-zero submatrix is changed like this. This implies that the number of non-zero of S changes because the short complement computed by this combination of these submatrices. More specifically, if we increase the hub selection ratio K, then the number of hub increases like this. And the number of non-zero of the H22 increase slightly, and the number of non-zero H12 and H21 decrease. The point is that the number of non-zero of this matrix product term decreased a lot because the inner matrices becomes sparse. So the number of non-zero of the short complement decrease. Let's check some experiment result about this. In this figure, y-axis indicates the number of non-zero of a matrix, and x-axis indicates the number hub selection ratio K. So, and blue line is for the number for the S, and yellow line is for this term, and red line is for the H22. So as you can see, as K increases, the number of non-zero of H22 increase gradually, and the number of non-zero of this matrix product term decrease a lot. So the number of non-zero of the short complement S decrease, and after some point, it increase again. So if we pick a hub selection ratio K that minimize the number of non-zero of S, then the efficiency of the iterative method on S is improved, and the space cost for S is also improved. Okay, let's check the second optimization. The second optimization exploits the preconditional for the linear system on S. The purpose of preconditional is to make the iterative method converge faster. In other words, the preconditional decrease the number of iteration to solve this equation. Actually, the preconditioning techniques are well studied in many literature, so you can think of it as a black box in this presentation. We exploit the incomplete LU decomposition as a preconditional, and using this preconditional, the implicit precondition systems are represented as follows. Thus that the solution of these systems and the solution of these systems are the same. So preconditioned iterative solver solve the implicit precondition system without the matrix inversion. Okay, let's check the experimental result. We aim to answer the following experimental question to evaluate the space space efficiency, and time and scalability. We perform our experiments on a single workstation with about 500 gigabyte memory, and we used a large-scale real-world graph dataset where the number of edges is from 500,000 to 2.5 billion. Okay, let's check the space efficiency. In this figure, y-axis indicates the memory usage for pre-processed data, and x-axis indicates the data set, and blue bar is for our method BEPI. And we compare our method BEPI with other pre-processing methods. As you can see, BEPI requires up to 130 less memory space than other pre-processing methods, and only BEPI pre-processes all data set and other methods fail. In terms of pre-processing time, BEPI is significantly faster than other methods, as you can see. And also BEPI is up to 9 times faster than other competitors in terms of query speed. Let's check the scalability of BEPI. We evaluate the pre-processing time and memory space and query time according to the number of edges. As you can see, BEPI processes 100 times larger graphs than other pre-processing methods, and BEPI shows the fastest RWA computation speed among other methods. And BEPI provides a real linear scalability in terms of time and memory usage. Okay, let me conclude this presentation. We propose BEPI, which is a fast and pre-processing and iterative approaches. Our main ideas are summarized as follows, and the main results are as follows. BEPI is a fast and scalable method for computing RWA scores, and BEPI requires 130 times less memory space and pre-process 100 times larger graphs than other pre-processing methods, and BEPI computes RWA score 9 times faster than other existing methods. Okay, thank you. This is the end of the presentation, and course and the data set are available at this site. Okay, thank you.
Any questions?
I think in the harp node selection part,
Yeah.
you choose some harp node, then the remain graph is there is no edges, right? Am I right?
Could you say again? I can't
So
hear.
if you reorder the nodes, right? You put the harp nodes to the in the matrix to the last matrix. Then in the big matrix there are no edges. Am I right? So in the H11 matrix.
Oh, sorry.
Yes.
Yes. Oh, you mean this part?
Yes.
Yeah.
I mean in this part, for the matrix, adjacent matrix here, there is no edges between the nodes in the H11 matrix, right?
You mean actually H constructed from this equation. Okay. H constructed by this equation, and this is an adjacency matrix, and this is the identity matrix. So in the SPI plot, so there is in the SPI plot.
Because see the graph is very sparse.
A sparse plot. This is actually the identity matrix plus adjacency matrix. Can you understand? Okay, we may discuss it at the poster session. Okay.
Other questions? Thank you for participating in this session.
Thank you.